In this partial fractions integral, we have an irreducible quadratic factor, and we have a linear factor. And so the proposal that we make is that this integrand can be rewritten as a sum of two simpler fractions. Now, over the quadratic piece, in general, we need a linear piece, ax plus b, to guarantee that this decomposition is possible. And over the linear piece, we just need a constant. So that's our proposal. And we're going to figure out how to break this integrand down into these simpler pieces, and then hopefully each of those is not too hard to integrate. So we're going to multiply by a least common denominator. Apply that to all three of these terms. And when I apply it on the left-hand side of the equation, it's going to cancel the entire denominator, giving me a 3x plus 4. When I apply it to this quadratic piece, the x squared plus 4 is going to cancel, and I end up with ax plus b times 3 minus x. And when I apply it to the last term on the right, the 3 minus x is going to cancel, and it leaves me with a c times x squared plus 4. So I'm going to go ahead and handle this one by collecting all the like terms on the right-hand side. So I want all the coefficients of x squared, all the coefficients of x, and all the constants separated out. And from this first product, I'm going to have an ax times a negative x, which gives me a negative ax squared. And in the second piece is c times x squared. So I have c minus a times x squared. Then I get my linear piece. From the first product, negative x times b. So I'm going to have a negative b times x from that. And there are no other, there's one other linear piece. There's a 3ax, so plus 3a times x. And there are no other linear pieces after that. Then I go to my constants, and here I have a 3b. And from my very last term, I have a 4c. Okay. So if this equation is going to be true for all x, then the coefficients on the left and right-hand side have to match up. So the coefficient of x squared is c minus a on the right side, and it's 0 on the left side. So I immediately get that c minus a equals 0. Then I do the same thing with the linear term, and I get that 3 on the left-hand side is equal to negative b plus 3a. And then I do the constants, and I get that 4 is equal to 3b plus 4c. And now I've got a system of equations, 3 equations, 3 unknowns. And I'm going to summarize my system real quick. That's c minus a equals 0. 3a minus b equals 3. And 3b plus 4c is equal to 4. And I'm looking for an elimination to start things out. So what I'm going to do is multiply the second equation by 3 and add to the bottom equation, and that will eliminate the b's. So I end up with a 9a and no other a's to add to, a negative 3b and a 3b, so those cancel, a 4c in the bottom equation, and then a 9 plus 4, or 13, on the right-hand side. I then combine this with the first equation. If c minus a is 0, that means a equals c, so I can make a substitution up here. I get 9a plus 4a, since a is equal to c, is equal to 13. That's 13a equals 13, which means a is equal to 1. That also means c is equal to 1 since a is equal to c. Then I can go back to any equation I want that has a b in it to find b. And I'm going to go to the middle equation. I have 3 times a, which is 1, minus b equals 3. In other words, 3 minus b equals 3, which means b is equal to 0. Okay, then I can plug all this in, and my integral has been transformed. This big rational expression broken down into 2 simpler pieces, ax plus b, so that's 1x plus 0, in other words, x, over x squared plus 4. And then my c is 1 and hopefully each of these pieces is fairly simple to do. So I have a little space down here in the corner to do these, and I'm going to break them up explicitly as 2 different integrals just to make some of the manipulations easier. And instead of 3 minus x, that's going to cause some interference with the chain rule. So I'm going to factor out a negative 1 out of that piece. That turns the denominator into an x minus 3. Now the first integral, if I put a 2 in the numerator, 2x is just the derivative of the denominator there. So I'm ready to do the chain rule backwards, and I get 1/2 natural log x squared plus 4. Notice that I don't have absolute value bars there because x squared plus 4 is always positive. And then my second piece is going to be a natural log absolute value x minus 3. And then I have to tack on my arbitrary constant plus c.